Hello, welcome. In this section, we will talk about a nonlinear model. If P of t denotes the size of a population at time t, the model for exponential growth begins with the assumption that dp over dt equals k times p. The rate of growth of population at any moment equals to some constant k times the population at that time, where k is some positive constant. In this model, the relative or specific growth rate defined by the quantity dp over dt over p is a constant k. True cases of exponential growth over long periods of time are hard to find because the limited resources of the environment will at some time exert restrictions on the growth of a population. Thus, for other models, the equation 7.2.1 can be expected to decrease as the population tree increases in size. Suppose an environment is capable of sustaining no more than a fixed number k of individuals in its population. Then it is reasonable to assume that the relative growth rate of the population starts out at when is small and approaches 0 when is close to k. In other words, we want a model of the form dp by dt over p equals some function depending on the population only, where the function f satisfies these two conditions. Initially, when the time was 0, f at 0 equals to the small k, the growth rate, and the value of the function f at the fixed number k equals 0. The simplest function satisfying these conditions is the linear function, whose graph is the straight line passing through the points 0, k and k, 0. We can verify that the desired function has the form f of p equals k times 1 minus p over the big K. The quantity k is called the carrying capacity of the environment. Now, the simplest assumption on f that we can make gives the form of the differential equation. dp over dt or p prime equals the small k times p times the quantity 1 minus p over k, as shown in equation 7.2.2. Around 1840, the Belgian mathematician biologist P.F. Verhulst, who lived in 1804 to 1849, was concerned with mathematical models for predicting the human populations of various countries. One of the equations he studied was the equation 7.2.2. Equation 7.2.2 came to be known as the logistic differential equation, and its solution is called the logistic function. The graph of the logistic function is called a logistic curve. We observe that if P is small relative to K, then the quantity P over K is small. And the equation dP over dt would be approximately equal to K times P. Since dP dt was equal to K times P times 1 minus the quantity P over K, if we assume that P is small relative to K, then this quantity is close to 0. So we have dP dt is close to K times P. That is, the logistic model behaves like the unrestricted growth model. But as P approaches K, then P over K approaches 1. Then the rate of growth of P, that is P prime, approaches 0, since this quantity would become 0. So the dP dt would be approximately equal to 0. Thus, the logistic differential equation exhibits both the property of rapid growth initially and that of saturation eventually. We also note that if the initial population exceeds the carrying capacity K, then the quantity 1 minus P over K is negative. Therefore, the equation says dP dt must also be negative, so the population decreases. The linear differential equation dP by dt equals K times P does not provide a very accurate model for population when the population itself is very large. Logistic curves have proved to be quite accurate in predicting the growth patterns in a limited space of certain types of bacteria, protozoa, water flies, and fruit flies. In this example, we will solve the logistic differential equation. P prime equals K times P times the quantity 1 minus P over K, subject to the condition P at 0 equals P sub 0, the initial population. Let's solve the equation. We observe that the differential equation has critical points 0 and K. Since the right hand side of the equation becomes 0 if and only if when P is 0 and P is K. We also note that the point 0 is a repeller and the point K is an attractor. Therefore, the constant solutions are P of t equals 0, and 0 being the repeller, this solution is unstable, and P of t equals K, and K being an attractor, it is an asymptotically stable solution. We also observe that the initial condition gives P prime at 0, the rate of growth at 0 initially equals K times P sub 0 times 1 minus P sub 0 over K. Now, if the initial population P sub 0 is smaller than the carrying capacity K, and the rate of growth of population at time 0 is positive, then we must have the quantity k positive. Similarly, if the initial population p sub 0 is greater than the carrying capacity, so we have this quantity negative, and the rate of growth initially must also be negative. The population tend to decrease. So we must have the quantity k also positive. So in every case, we see the k should be a positive quantity. To find the non-constant solution, now we rewrite the equation as shown here. Now the left-hand side of the equation can be written in this form, whereas the right-hand side takes the form k times dt by using the partial fractions. Now integrating both sides, we have this equation. In the left-hand side, we have the natural log of absolute value of p over k minus p, which is obtained from here. And in the right-hand side, we have k times t plus some arbitrary constant, c1. And by taking the exponential, we get the equation 1. Here, a is defined to be equal to e to the c1, which is strictly positive. Now, if we have the situation that the initial population is smaller than the carrying capacity, then the initial condition gives the value of a as 1 over the quantity k over p sub 0 minus 1. Therefore, equation 1 becomes this equation, and we solve this equation for p, we get this equation, and then we substitute the value of 1 over a from here we obtain the equation. This is the solution of the logistic differential equation subject to the initial population p sub 0 with the situation that p sub 0 is smaller than the carrying capacity. Similarly, if the initial population is greater than the carrying capacity, then the initial condition gives the value of a as shown here. Therefore, the solution of the logistic differential equation takes this form, where p sub 0 is greater than k. As said before, the graph of equation 7.2.2 is called the logistic curve. We note that in either case, the limit of the population as t approaches plus infinity is k, the carrying capacity, since the limit of the term e to the negative kt as t approaches infinity, with the assumption that k is positive, is 0. Some observations. Suppose that a population at any time satisfies the logistic differential equation, and that the initial population is p sub 0. Then, if p sub 0 is equal to 0, the population stays at 0 at all times, since this solution satisfies the initial condition p of t equals 0 for all time later than the initial moment. If the initial population is something positive, but smaller than the carrying capacity, then the population increases and approaches the limiting value k asymptotically. The population increases most rapidly at the instant of time when it reaches k over 2, as by the previous exercise. If the initial population is equal to the carrying capacity, then the population at any later time remains at k, since this solution then satisfies the initial condition. If the initial population is greater than the carrying capacity, then the population decreases and approaches the carrying capacity k asymptotically. Let's have a look at an example. A fish farm is stocked with 100 fish. Suppose that the fish population satisfies the logistic equation and that the carrying capacity of the pond is 2000. Find an expression for the fish population after t years. If the number of fish increased to 250 in the first year, how long will it take for the fish population to reach 1000? Let's see the solution of this example. Using equation 7.2.3, we see that the population after t years is given by this expression. Here, the carrying capacity k equals to 2000 and the initial population of the fish, p sub 0, equals to 100. So the expression simply becomes p of t equals 2000 over the quantity 1 plus 19 times e to the negative kt. Now to determine k, we use the initial condition that after 1 year, the number of fish is 250. This leads to the equation where k is the unknown growth rate. Now solving this equation for k, we find that k equals the natural log of 7 over 19, which is equals to 0.9985. So the model takes the form p of t equals 2000 over the quantity 1 plus 19 times e to the negative 0.9985 times t. This is the required expression for the growth of fish, satisfying the logistic differential equation. Now to solve the part B of the question, let us assume that it takes t years for the fish population to reach 1000. That is, p of t equals 1000. Now to find t, we solve the following equation. Which gives t equals natural log of 19 over 0.9985, which is approximately equal to 2.95 years, which represents the time when the population grows most rapidly, since the half of the carrying capacity k over 2 equals 1000. The direction field and the behavior of the solution curve of this model is given in the following figure. Exercise. Some population are subject to seasonal fluctuations. The population in a vacation resort serves as one example. A model for describing such situations may be given by the following differential equation. dp over dt equals k cosine of t times p, where k is a constant and t is measured in months. Find the solution of the differential equation subject to the initial condition. Let k equals 0.2 and plot the graphs of the population for the initial population 400, 500, and 600. What happens to p for large values of t? Meaning, calculate the limit of the population when t approaches plus infinity.